Alright, let's start. So we start with this lecture 1 about the intro and the basic linear algebra stuff, and did I ask you to watch the online videos of 4 different perspectives of matrix multiplication? So it was part of the lecture video that I posted through the announcement. So if we have 2 columns, I think I mentioned it in the first class briefly, but if we have 2 classes and then we have a vector on the right, and then how many entries do we have? So we have 2 entries in the vector, I mean the column vector on the right, and then suppose it is 6, then 8, and then we know that the first entry is computed as the inner product between these 2 row and the column vector. So 1 times 7 plus 4 times 8, and then 2 times 7 plus 5 times 8 and 3, right? So this is the typical way of computing the inner product, but this matrix vector multiplication can be viewed as this. So this part is just 7 times this vector and 8 times this vector, right? So that way so we have 2 columns on the left, and the vectors on the right is actually providing the linear combination coefficients, right? And so in this manner, the resulting vector will be always represented as the linear combination of these 2 column vectors. And so what we can know from here is that, so here for whatever values of these 2 linear combination coefficients, the resulting vector will be always belonging to the span of these 2 vectors, right? So that means, so originally this vector exists in the 3-dimensional space because simply we have 3 numbers, right? And so if we represent it, 1, 2, 3 is somewhere over here, and 4, 5, 6 is somewhere over here, and then we have these 2 vectors, and given these 2 vectors, the resulting matrix vector multiplication will not go beyond the space or the thin plane spanned by these 2 vectors, right? So in the entire 3-dimensional space, the linear combination, all the possible linear combinations of these 2 vectors will be just thin plane, right? Does it make sense? So that is the notion of the span, right? So let me see if I can give you some example. Okay, I will just draw my figure. So if we have these two vectors, and then what is the linear combination of these two vectors by using the coefficient as 1 for each vectors. So we have a v1 and v2, and then what is this resulting point? The resulting point will be this guy, right? And then suppose we change the linear combination coefficient as 1 times 2, and then what will be the corresponding point? We will just do the scalar multiple of the second vector, and then still, yeah, draw this parallelogram, and then this guy is the resulting point, right? So if we change those two linear combination coefficients as any real numbers, and then the resulting point will cover the entire plane, yeah, spanned by or stretch it by these two initial vectors, right? But at the same time, the resulting vector through this linear combination of the two given vectors cannot go beyond these two, the thin plane spanned by these two vectors, right? So we are originally living in the three-dimensional space, but we are only given just the two vectors, and then all the possible linear combinations spanned by these two vectors will be just thin plane, right? So this matrix vector multiplication, the resulting point, cannot exist outside of this thin hyperplane, right? And also this span is defined formally as the point, the set of all the possible points, as the linear combination of these two vectors, two given vectors, when using linear combination coefficient as any real numbers. Okay. And also, what if we have just a matrix on the right instead of a vector? So in this example, we had a 7 and 8, right? And then now we understand that the resulting vector is the linear combination of these two vectors by using the linear combination coefficient as 7 and 8, which is contained in this vector. But what if we have this kind of matrix on the right as well instead of just a vector, right? So in this case, okay, so we can also still think of this matrix multiplication as the column combination, and then let's think of this resulting vector, and then how many columns do we have in this resulting vector? Resulting matrix. So we have 2 columns as a resulting vector in this matrix, right? Because so if we do the multiplication, and then we will generate the scalar value over here, then here and here, right? And then also if we do the multiplication like this, and then we will have these 3 points, and so we have 2 columns in the resulting matrix, right? And then this first column, if you do the computation, and then this first column is exactly the same as this, so which means we have these 2 columns, and then the linear combination coefficient of 7 and 8 will produce the first column. And then what about the second column? It is also represented as a linear combination of these 2 column vectors, but using different linear combination coefficients of 9 and 10, right? So, so does it make sense? Okay. So, if we have the matrix on the right, so for example, suppose we have some other numbers, okay, and on the right matrix, and each column provides its own set of linear combination coefficients to produce each column in the resulting matrix, and thus those vectors will always belong to the span of these two two ingredient vector or two basis vector that we have on the left, right? So so those two columns will still remain within the hyperplane or within the plane spanned by the two vectors, right? Okay, so this slide is discussing about this aspect about the matrix vector or matrix multiplication. So if we have a matrix on the left, and then suppose we have n different columns, and then we have the vector x on the right, and then we will have n different numbers, right, as a column vectors, and then that will be the linear combination of the columns on the left by using the linear combination coefficient of these x1 through xn, which is in the vector on the right. So any questions? Okay, so just to make this discussion a little bit more interesting in the perspective of a neural net. So suppose we have maybe 3 different nodes, and then three different nodes as an input and 4 different nodes as an output, and then let's think of the fully connected layer over here, and then this vector y belonging to 4-dimensional space and 3-dimensional space for the vector x as an input. Then we have a matrix W, and then x will have this 3-dimensional vector, and W will have the size of a 4×3, right? Okay, so in this case, the resulting 4-dimensional vector is represented as a linear combination of those 3 column vectors, right? And what is this? What are these 3 column vectors corresponding to? So that is corresponding to the weight of. And suppose we have the coefficient as 1, 2, 3, 4. Okay, so in this case, these coefficients are 1, 2, 3, 4, right? And then 5, 6, 7, 8. So that is the linear combination coefficient. Corresponding to the edge starting from this second input node, right? So 5, 6, 7, 8, right? Okay, so 9, 10, 11, 12 to make this example complete. Okay, so in this particular case, so if we have a 3 nodes as an input and 4 nodes as an output, and then the question that I want to raise is whether the resulting 4-dimensional vector, these are resulting vectors, can all of these possible 4-dimensional vectors cover the entire space of this 4-dimensional space. So in other words, suppose we provide any possible 3-dimensional vectors. So you have freedom to put any numbers in this 3-dimensional input vector, and we will have this linear transformation matrix, and then the set of all the possible resulting output vector, okay, output vector, yeah, they will not cover the entire four-dimensional space in any cases. So it is impossible, right, to cover or fill out the entire four-dimensional space, right, because we have only 3 vectors, and the resulting vector will be always represented as a linear combination of these 3 vectors, right? So just like the situation where, I mean, in the 3-dimensional space, if we have 2 vectors and then given any particular 2 vectors, and then the span or all the possible linear combinations of these 2 vectors, yeah, has no way to cover the entire 3-dimensional space, right? Okay, so so if we just if we have a output layer which has the more number of nodes than the input layer, and that means the resulting output vectors will not be will not have the all the possible four-dimensional numbers, and then that limited number of that limited set of four-dimensional vectors will be propagated, will be forwarded, forward propagated through the layer networks, right? So, I'm not sure how meaningful it is, but if you become familiar with this geometric sense about these vector kind of locations and the layout kind of thing, and then it might be easier to understand what happens in inside of the neural nets. So okay, so and also from the perspective of a machine learning and maybe some of the mathematical perspectives of the data analysis, given our input, all the possible input vectors, and then the output will be limited to a smaller set compared to the entire four-dimensional set, and that set is called sometimes it's called manifold. Okay, manifold. Although manifold involves non-linearities, possibly. So it is not restricted to just a linear kind of subspace. That is just a straight. In the case of a plane spanned by these 2 vectors, and then that plane will be just straight. So it's not curved structure, right? But when talking about the manifold, we assume that the actual set of the resulting output vectors, that is the main key concept of the manifold, or that is a rough definition of the manifold, and we assume that possibly this manifold can be this kind of curvilinear kind of structure, and but you can roughly think of this manifold as the actual set of the resulting points when giving any possible input vectors through this function. Okay. Okay, and then you can also think of this from the perspective of maybe generative models of the deep learning. So in the case of generative models, why is it called generative models? Because it's generating some data, and that data is typically maybe a particular sentence in the context of an NLP. So when doing the machine translation, that is one example of a generative model, because it's generating output sentence, right? But what is not a generative model? Typical classification methods. Classification techniques is not called the generative model, because that is producing the actual data, but it's producing maybe some compact, just a few numbers in terms of maybe the most possible class label as a prediction result, or the output of the neural nets, right? So another generative model example is just maybe generative adversarial networks that can maybe generate the particular images, right? So in that case, in terms of the number of input nodes and the number of output nodes, typically generative model is producing more number of outputs, more number of nodes in the output layer than the number of input nodes in the input layer, right? Because typically in GAN, so we have some noise vector or latent vector, for example, starting from 4-dimensional vectors, and then we will typically go through the deconv or deconvolution and things like that, and so the resulting output will have a lot more numbers than just the 4, which is the number of nodes in the input layer. So if we generate the 32 by 32 and also this kind of RGB channels, having RGB channels, and then from 4 different numbers, we are mapping these 4-dimensional vectors into much higher dimensional vectors, right? So if we just think of just one long and thin vectors as a rearranged form of this 32 by 32 by 3, okay? So in this case, if you apply this kind of notion, and then starting from any possible 4-dimensional vectors, the mapped point or the resulting vector in this much higher dimensional space, and then collecting all the possible output vectors, and then they will only cover some small regions in this much larger high dimensional space, right? Okay, but so that means after learning these generative models, through some particular the optimal parameters that we obtain at the end of our training process, and then that will define those kind of basis vectors or particular subset of those output points, right? Where this subset of an output points should be placed in the 4-dimensional, this much higher dimensional space. So these parameters will carefully define that kind of where this subset of these resulting vectors should be placed. But for whatever learned values of this matrix W, we cannot represent all the possible resulting vectors, right? So that actually makes so in that case, it may sound that this model is quite limited, because in that case it may not be able to represent all the possible images that exist in our real world, right? So if we think of this 32 by 32 by 3 as an output image, then we cannot represent all the possible output vectors, right? Starting from this much lower dimensional input. But that is typically okay, because in real world or our actual data will have also that kind of limited subset of this kind of subset of resulting vectors. That is not, that is much smaller than the entire points existing in this high dimensional space, right? So let me give just one intuitive sort of example over here. So if we generate the some face images. Okay, so in this case, yeah, we can roughly think that, of many different restrictions or constraints, so that this image can be realistically some facial images. So, for example, suppose, let's think of the pixel that is placed inside of the facial regions, and then the variations of facial colors will be also limited, because typical people, if they are not alien, then just the humans will have some specific facial kind of color values, right? So it cannot be pure red, it cannot be pure green, or it cannot be pure black or white, and so on, right? Although it can be a little bit beige color and so on. So that way, we can represent, we can easily think of this kind of intuitive constraint that this pixel cannot be any kind of RGB values, right? So that way, already our realistic set of, the set of all the possible realistic data, that also has, that is also placed or existing in only a limited regions, or some subset of the entire possible high-dimensional space, right? And also, we can think of some other constraints as well. So that is like relative relationships. So for example, so if we had the if we had the black color as the so what is called the circle in our eye, pupil. How does it spell? Okay. Okay, so suppose the color corresponding to here was black. And then in that case, it means that this, like the counterpart, the same regions in another eye within the same person should be the same color, right? Although some people may have different colors for those two regions, but that is roughly another kind of constraint that we can have, right? And also, in general, ignoring this specific case of only the facial images, and then let's just extend it to a much larger set of all the possible realistic photo images. Okay, it is not just a facial images, but just realistic images. So in that case, what kind of constraint can we think of? So in that case, let's think of these two adjacent pixels, right? So in this case, we can think of some kind of restrictions or just kind of particular characteristics that those two pixels should also have some small number of variations. So suppose this pixel was maybe brown, and then in realistic photo images, the adjacent pixel cannot be really like quite different colors, or maybe pure green, right? So it may not be exactly true, but what I'm trying to the point that I'm trying to make is that in realistic images, so those adjacent pixels is likely to belong to the same object that has the consistent colors. So in that case, those two different two adjacent pixels cannot have really large variations or differences between the two, right? So that way, we can think of our kind of restrictions to become a realistic images, and then that constraints or restrictions is actually learned. I mean, that way those restrictions will make the entire images of realistic photos into a smaller regions out of all the possible vectors in this high dimensional space. Okay, and this W, you can think of this W. yeah. This W will be a way to map to that proper subspace or sub-regions. Okay. Okay, so in general, our realistic data, okay, and their subsets out of this entire high dimensional space, and that subset is called this manifold. Okay. Any questions so far? Does it sound interesting or not? No.
W is depends on.
Oh yeah, right. That's right. So in the case of GAN or generative adversarial networks, so this W is trained, or I mean, the optimal value of W is determined in a way that, so we have a set of our own realistic photo images, right? And their photo images will form some subset or its own manifold, right? Out of this entire high dimensional space, right? And then suppose, so that manifold is completely determined by our existing point. I mean, suppose we have 100 different images, and then each of 100 different images will be represented one particular high dimensional vector in this space, and then we have 100 number of vectors, right, in this high dimensional space. And then you just draw these 100 points, and then you can think of these subset or these sub-regions, sub-regions formed by these 100 different points, right? So in this process, it doesn't involve any of learning, right? So we just mapped our particular images into one particular point in this pixel high dimensional space, right? And that subset or that manifold, if W, I mean, starting from the random vector, random 4-dimensional vector, and then let's map it to particular points in this high dimensional space through some learned W matrix, and then suppose we generated 100 random vectors in this 4-dimensional space, and then map each of them into one particular point in this pixel space, and then they will form their own manifold. And then let's think of these two manifolds and compare between them, and then the adversarial network. I mean, adversarial part of this discriminator. I mean, counterpart of this generator, which is our discriminator, is actually determining whether these two manifolds are almost matching or almost the same, so that it is quite difficult to distinguish between them, right? So it's like, I mean, the process of learning W can be viewed as this aligning the manifold of these generated points into the existing manifold of the already given realistic data that we have. Did I answer the question? Okay. Any other questions?
Other activation functions or nonlinear sums biases.
Right.
It's not nonlinear. So why do we do linear combination at the first time? Can't we do like other sort of stuff like multiplying two later or doing nonlinear stuff?
yeah, we have a freedom to use more complex transformations instead of this linear layers. So typically the typical way of designing our neural net is concatenating the linear layers into nonlinear layers, and after that, it is followed by the another linear layers and so on. So we can design. So in this case, the nonlinear unit is typically used as a simple function over maybe ReLU, sigmoid, and so on, and typically they are fixed. That doesn't involve any parameters, although we use more complex nonlinear units that involve some parameters to learn. For example, like maybe ELU or leaky ReLU and things like that. So those are involving some parameters to learn. But anyways, so that seem to be quite still small. There seem to be quite simple models, right? And then linear layer is also quite simple model. So we can also think of one layer that involves maybe second order term as a quadratic functions, or maybe cubic, or maybe sinusoidal kind of mapping and so on. But the main point of using this simple linear and also simple nonlinear and their combinations as our main our main design of our neural net is because the main reason for that is because by using those simple kind of pieces of linear and nonlinear and their sequential kind of concatenations, that will be able to represent any given manifold that we want to represent, or any kind of function mapping. That can represent any given kind of complex shape of our manifold. Okay, so that is quadratic.
Or are there any limits that come when we use more complex functions?
Are there any limits when using more complex? If we use more complex functions as our base unit, and then the representation, our model model capacity, that means what kind of model we can represent, what the total number of different function shapes that we can represent. In that case, if we use more complex units, and then we have more powers to represent more complex functions, or complex mapping, or complex manifold, and so on. But in that case, the trade-off, or the things, the aspects that we have to sacrifice is that we need more number of parameters that are difficult to learn. So in reality, we always have to learn these manifolds or these mappings from the limited data, right? So the typical figure of, right? So suppose we have this limited number of data, and then we can roughly interpolate like this. And so once we form this mapping, and then we now perform prediction. So initially we have a 1 times 1,3 and maybe 3,5, and those limited number of training data items. But once we learn this mapping, and then this mapping will allow you to map any other, any given x values. So if x value was maybe over here, and then our learned model will have the prediction output as this value, right? So and then if our model capability, our model capacity is small, and then for example, like linear models will only be able to represent this straight lines. So in that case, it will not properly fit our limited number of data. And then if our model is more complex, and then we know that this overfitting can happen, right? So in general, if x increases into some value around this regions, and then yeah, the prediction should be predicted value should be higher, but in this overfitted model, it is saying that. So this kind of thing can happen. So our entire goal, I mean, entire goal of machine learning is to perform as much as possible, or yeah, performing the best for the unseen data. So what does that mean? What does that mean to perform well on the unseen data? So that thing is, we have to be able to reconstruct this kind of function mapping, or the kind of manifold, okay, that the real data has from only the limited number of data, right? So yeah, so we are just given those particular, I mean, the finite number of data points, right? So, but from these points, yeah, we think of some continuous subspace or the manifold, right? So we have to be able to reconstruct them properly, so that for unseen data, yeah, we can have a better mapping, or yeah, most accurate mappings, right? Yeah, so the main point of using, and back to the question, the main point of using simple linear and the simple nonlinear layers and their concatenations as our main kind of design of our neural net is that even when using those simple models, when concatenating them, and also when using the sufficient number of hidden nodes and the number of hidden layers, then yeah, we can represent any functions, okay? Any manifold, any complex manifold. Okay, so that is the main idea. Any other questions? And also, yeah, you can ask the questions in Korean. So feel free to ask, yeah, your questions in Korean. So yeah, I mean, yeah. So let me add yeah, some other, I mean, more comments. I mean, yeah, related to that aspect of being able to represent any given functions or any given manifolds by using this yeah, linear and nonlinear and so on, is called, yeah, I don't have, yeah, I didn't study carefully this, but if you are interested, and then you can look at something called universal approximation theory or theorem. Okay, I believe yeah, this theoretical background, yeah, is related to this neural net capability. So yep, and also if you're interested, and then you can also think of this, yeah, representing any kind of, yeah, functions. So suppose we have this kind of functions, and then how can we approximately represent this function by using the linear and also nonlinear layers, when using maybe nonlinear layers as a ReLU, for example. So in this case, yeah, you can roughly think of the ReLU as this. So we just approximate it as maybe piecewise linear. Okay. So ReLU is like, intuitively, ReLU is like cutting the infinite straight line, yeah, from one side. Okay. So if we apply ReLU over here, and then even though this original linear representation or function will be just a straight line that goes infinitely through both directions, but if we just apply ReLU, and then it is just a cut here. And so yeah, we can use that kind of a line segment. And also in the case of this line, and that line is formed by another node in our linear layers. So for example, if we have an X over here, and then this is maybe 2 and maybe 3, which is like 2x plus 3. So suppose that is this line, and then we form this node, and then also suppose within this layer, this line is having this form. Okay, so in this case, yeah, we can have its own slope and the bias term to form this point, right? And then we can, we apply ReLU over here and over here, right? And then using these line segments that goes only through one direction, and in other side that was cut by the ReLU layer, and then by just also linearly combining them in the next linear layers after going through the ReLU, and then we can just stitch them so that we can represent any particular functions like this. Okay. Although it's a quite hand wavy or quite vague explanations, but yeah, you can actually make your own examples and to represent some arbitrary functions. Wow. Why is it less? Okay, so so in this ring type of neural nets, although it's not a regression problem, but classification problem. And then this is the example when using the nonlinear layers as 10H. Okay, 10H. 10H is like, they are softly cutting from both edges. Anyways, so let me just change it into ReLU, for example. Okay, so you can see this straight kind of line segment that forms our decision boundaries, and where does this line segments come from? Okay, so that is coming from the linear, straight line that was produced in the first layer, and we apply the ReLU, right? And then it will cut from one side at a particular point, and then those 반직선은 영어로 뭐라 하죠? 한쪽으로만 뻗어나가는 네? 반직선? semi-infinite line? Anyways, so they will produce the line that goes infinitely into only one side, but not on the other side because that was cut by our ReLU. And then by stitching them and linearly combining them, and then in the next layer, then you will produce those stitched two different stitched version of these decision boundaries, and then it will finally be linearly combined in order to create this boundaries. Okay, so it may be a little bit difficult to draw this example. Because it may involve a much higher dimensional space, because like in this second layer is already involving 4 different nodes, and so in this case it is mapping from 4-dimensional vector into 2. So it might be a little difficult, but you can actually get a rough idea about what we are doing by just concatenating linear and the nonlinear layers and so on. Okay, so but let me just add one more comment about the case where we used 10H or sigmoid. Okay, so if we use the sigmoid and then we know that, I mean ReLU, and then we know the ReLU activation function is like this, and then sigmoid is, I mean suppose we use the 10H and then like this, right? And so so this part, I mean this part is the cut regions, right? So if our output given y equals 2x plus 3, and then if it is negative values, and then that is the region that is cut, right? Okay, but what if we just use the straight line of y equals x, and then that will just produce this result as it is without changing anything, right? So this guy, yeah, when thinking of this part, when using this horizontal line that is just along this our x-axis, so that is completely cut, entirely cut the negative side, right? And then this part will just make it survive entirely, right? So that is not cutting at all. And what about this guy? This guy is cutting like smoothly, right? Cutting like smoothly. So it is a little difficult to draw, but so this part is attenuated or smoothly cut or gradually cut more and more, and also this part as well, it is cut, yeah, smoothly, right? So it's like, yeah, the decision boundaries are something like this kind of thing, right? But still, at some point, it is almost equivalent to just being cut entirely, and also being cut entirely over here. So that is producing the line segment that has the finite ends on both sides, right? In the case of ReLU, it is cutting entirely on one side, and then the other side is not cut at all. But in the case of sigmoids, or maybe 10H, it is like cut, yeah, cutting on both sides, but quite smoothly. Okay. So it's also quite hand wavy explanations, but so that's why when using the ReLU over here, and then we obtain this. So it's okay. I just grab it. But in this case, we roughly have 3 linear decision boundaries, and they are kind of curved at the end of these 2 sides of this line segment, right? So it is almost the same of like stitching multiple different linear separation decision boundaries, and then at each end of the line segment that is attenuated or curved through this sigmoid operations. Okay. Any questions so far? Okay, then back to our class material. Okay, so given this linear mapping defined by our matrix W and maybe vector X as W times X, right? Okay. So in that case, so let me just discuss a little bit more about the term. So you guys know the notion of the span, right? So the span is also called the range of a function or range of our transformation. So range has the what's the Korean term of this range? Sure. Of a function, right? So it's all the possible actual outputs of our function, right? So in the linear transformation, our range of this transformation or function, when it is linear, and then that is always represented as this straight kind of a plane, right, spanned by the given ingredient vector, okay, that is given in the matrix on the left, right? Okay, so that is the range, and that is the same as the span. And what about this null space? Null space. Null space is okay. So in this case, yeah. Okay, let's think of this case, although it's a little bit messy. But what is the input vector dimension? Input vector is a two-dimensional vector, and then it is mapped into three-dimensional vectors, right? Output is three-dimensional, and input is two-dimensional. And the output space. The null space is subset of R3, right? R3. So the resulting vector is of course existing in the three-dimensional space, but that is the definition of range. But what about the null space? So that is subset of R2, which is about the input subset of the input vectors. Okay, input vectors, and that subset of an input vector defined by the null space is described as the set of vectors that will produce the linear transformation output as 0. So suppose we have this particular matrix as our mapping matrix, and then in this case, this 0 is a vector, 0 vector, right? So in this case, so collecting all the possible vectors, input vector in the two-dimensional space that will produce the 0 output. So that is the definition of the null space. So in this particular case, what is our null space? One example is a 2 and 1, right? So 2, 1 is one member of our null space, right? So in that case, so typically this null space is also spanned by some set of vectors. So in this particular case, so if 2, 1 is one member of our null space, and then of course 4, 2 is also belonging to the null space, right? So basically, if 2, 1 was our point in the null space, and then so this is 2, 1, then this straight line spanned by this single vector. So all the points lying in this straight line will be also belonging to the null space, right? And this null space can this null space be 2 or more dimensional, right? So which means, can this null space be spanned by maybe multiple vectors, like in the three-dimensional space, for example, in this particular case of mapping from three-dimensional space into four-dimensional space. In this case, is it possible that our null space, which is originally in this three-dimensional space, be spanned by 2 vectors? Okay, 2 vectors, like 2, maybe 2, 1, 0, and maybe 3, 4, 5. And the span of these 2 vectors, and any linear combinations of these 2 vectors will also be belonging to the null space, right? Yeah, so it is possible, okay, although I didn't give an example, but so I may give an example shortly, but the point that I want to make when thinking of this null space, okay, so this null space, I mean the vector belonging to the null space is actually, you can have an intuitive understanding about this null space as like those vectors belonging to the null space is kind of insensitive, or your neural net, in the case of this neural net defined by the linear layer, your linear layer will be blind about this null space. So that means like this. Suppose you have a height and a weight, and then you want to extract out some meaningful feature for your own task, and your own task is to classify the diabetes. So whether a person has the diabetes or not. Okay, so it's a binary classification, right? So in that case, one potentially useful feature will be like the degree of being like overweighted, right? How a person is overweighted, right? In that case, overweighting is defined as the ratio between maybe height and weight, right? Or the overweighting rate, degree of overweight is defined as, for example, like this: height, maybe weight minus height plus 100, for example, and then it is like 75 kilograms and your height is 175 centimeter, and then you will exactly have 0 overweight value. And then suppose you are 85 kilogram and then with the same height, and then you have the degree of an overweight as 10, right? So that would be kind of a useful feature that can be utilized for our diabetes classification, right? So this representation is exactly the feature that we can represent through our linear layers, right? So weight times 1, height times -1, and then bias times 100, right? So in this case, what is insensitive, or what is the blind? What is the blind regions? So that blind region, I mean, you can roughly or intuitively think of it as this. So so suppose you obtain a 0 as an output, which means a 0 degree of overweight. So do we have just one single example or one single input feature vector that maps into 0, or do we have a multiple different input vector that will still be mapped into the same value of 0, right? So it's like so it should be weight and the height, okay, right? Okay, so 85 and 185, and then that will produce 0 as well, and then maybe 60 and 160 will also produce 0 value, right? So in that case, you can easily see that this is 0 value, okay, 0 value, or this output value is insensitive. I mean, they cannot discriminate or distinguish between these two input cases, right? So that way I mentioned the term of maybe blindness of your neural net or your mapping, right? So what is the blindness? So when x is increasing with 25, and then y is increasing 25, and in that case, it is blind to that kind of increment, right? So given a particular vector of an x1 and x2 as your feature vector, although we have a bias bias value as 1, but let's just ignore it for now. Okay, so given this input vector, and then suppose we have a mapping through this linear transformation matrix of W. Okay, so in this particular case, yeah, we may have some other nodes, but let's just also ignore some other potential nodes in our output layers. And so our output layer is just only having one node, and then what is our W? So W is like, so it was weight and height, and 1 and negative 1. Okay, 1 and negative 1. Okay, so in this particular case, so let's apply the definition of the null space of AX equals 0. So in this case, in the previous example, so we had two vectors, and then we tried to make them as 0 through some linear combination coefficients, right? So 1 and 1 was our answer, 2 and 1 was our answer, right? And then maybe scalar multiple of this 2 and 1 is another possible solutions. So what about this case? So we have these two column vectors still, although each column vector is just a scalar one. And then what is our one example or one input point belonging to the null space? It is like 1 and 1, right? So this 1 and 1, and the scalar multiple of this is actually blind from our neural net or this mapping, right? So what is that? So in this particular case, given a one vector, if we add scalar multiple of 1, 1, and in this particular case 25, 25, if we add it, and then that changes is not sensitive, or neural net doesn't know about that changes. What I mean by that is that, what I mean by the neural net not knowing about it is they produce still the same output, right? Okay, so that is kind of intuitive understanding about the null space. And then more exactly, so in this particular case, the null space is not only just a mapping. The input vector is mapping into 0, but it's actually combined with some existing or pre-given vectors, just like this case. So in this case, so 60 and 160. Okay, so this bias is actually let's just ignore this bias, and then and this, and this is our W, and this is a current input feature vector, right? And then the mapping will be maybe 100, negative 100, right? Okay, so in this case, W and X equals negative 100, and then suppose W and X plus the point or the one vector in the null space, and that suppose that vector is maybe A, and in this particular case A was 1, 1, right? Because that is producing 0 when multiplied with the A, right? So if you found such an X vector, and then you can freely add that X vector into whatever other vectors. So in that case, that X vector is now our A vector, right? So in this case, suppose we have some scalar multiple as K. So in this case, this is our new input. So here X is what? 60 by 60, 160, and K times X is 85 and 185, okay, by just adding 25, 25, right, corresponding to this part. And A is 1, 1 belonging to our null space, right? So in this case, if we just evaluate this this expression, and then we will obtain this, and then W times A will be always producing 0, right? So that doesn't change the existing, previous output value, right? So the null space is not just producing, null space is not just a vector that produces a particular value of 0, but that value can be just freely added to whatever existing or previous vectors, so that the output doesn't change at all, right? So that way, neural net is kind of blind about this particular vector of an A, right? So yeah, so that particular vector can be viewed as kind of a direction, because whatever scalar multiple of that particular vector or that direction will always work as the vector in the null space. Okay, so any vector, which is a scalar multiple of this particular vector A, in this particular case 1, 1. So that is the blind kind of thing. Okay, and okay. So typically, so suppose our input dimension is 3, and then our output dimension is 1. So it's a W and X. So in this case, what is the dimension? What is the number of vectors that will span the null space? So again, the null space can be just spanned by a single vector in this particular case. So that single vector was 1 and 1, and in this case, where is it? So in this case, 2, 1 is one single vector, and in this particular case, there is no other. So there is no other directions that belongs to the null space. But suppose 1, 2, 3, and the vector, and W and X. Let's think of this particular example that maps R3 into what? R1. So in this case, the dimension of the null space, or the number of vectors that spans the null space, is actually 2, right? So how can we make 2 different directions belonging to the null space? Yeah, maybe 1 and 1, -1. So that is one direction. And then maybe 2 and -1 and 0, right? So you can easily see that those 2 vectors are also belonging to the null space, and through this something called the superposition property or something like that. So that is like, so let's call this vector as A1 and this vector as A2, and then simply the linear combination of these 2 vectors will still produce 0 output, right? Because if you evaluate it, if you just rewrite it, and then you can easily see that this produces a 0 vector, right? Okay, so in this case, our null space is spanned by these 2 vectors that has different directions, right? So in the 3-dimensional space, then we have these 2 different vectors that has different directions, and then any linear combination of these 2 will also belong to our null space, right? So in that case, the insensitive vectors or the blind direction from our neural net or our linear transformation actually has this kind of 2 directions. Okay. And also, it is related to something called the normal vector in the hyperplane. So what is the normal vector? So normal means perpendicular, okay, or orthogonal, okay, having a 90 degree as an angle. Okay. So in this case, it is like this. So suppose this vector as W transpose. So originally W is 1, 2, 3, and then W transpose X should be 0, right? So that is the condition, that requirement to satisfy the null space for vector X, right? So in this case, what is the condition to satisfy for these X? X should be orthogonal to this vector 1, 2, 3, right? And so all the possible points that has the 90 degree angle with this 1, 2, 3 will belong to our null space, right? And so, yeah, this 1, 2, 3, which is our linear transformation parameter. So we have, yeah, initially there is a three-dimensional space, and then we have like the vector that is pointing to 1, 2, 3, right? And then let's just collect all the possible vectors that has the 90 degree angle with this vector, right? So this is the direction, and then we can easily obtain another vector, right, having a 90 degree angle, and also being different directions. I mean, having different directions from the first, I mean, previously found vectors. We can also easily find another vector having different directions that still has the 90 degree angle, right? So this vector and this vector will also satisfy all of them, right? So we can easily find these two different directions, okay? And spanned by these two different vectors, okay? That will be our null space. And what is that null space? So that is this plane, right? Like this, okay? That is perpendicular to this single line, right? So entire hyperplane, or entire plane spanned by this this plane is kind of blind direction from our model, and that blind direction is, I mean, if we just extend this this case, so this is related to like a linear separation boundaries, right? So if we have a support vector machines or maybe logistic regression that still has the linear decision boundaries, and then the linear decision boundaries will always be represented as that parameter vector times the input feature vector as that inner product thing, right? Although we have a bias, but we can always include it, add the bias into our feature vectors by just adding one more dimensions. Right. Okay, so so in this case, suppose we have a 10-dimensional space, and then suppose we created or we trained our SVM or logistic regression that still has the linear decision boundaries. And in that case, what is the dimension or dimension of this hyperplane of the null space, or the which is blind from our neural net? So that is always 10 minus 1, which is 9-dimensional space, right? So one linear classifier is blind just to the 9-dimensional space, and that is only sensitive to 1-dimensional space. And then if we construct the multiple linear classifiers or linear feature extractors within one layers, so in this case, it is corresponding to like having 3 nodes as an input and then one output node. And then what about having another node that is having its own linear combination? Okay, and then in that case, we are covering, we removed one direction from this blind kind of null space. 9-dimensional space will be reduced into 8-dimensional space, and so on. Okay, so this blindness. So let me add one more comment before having a break. But yeah, this kind of blindness is not always a bad thing. Okay, it's not always the bad thing. Why? So, I mean, diabetes, is really, I mean, when predicting whether a person has a diabetes or not, that should be really insensitive to a particular height or weight value. So, for example, I mean, as far as I know, the taller person has the more probability of having diabetes, or maybe shorter person has more probability of having diabetes. So there is no such such kind of observations that is found, right? So it is false, right? It is false. So diabetes is not related, or that is not dependent on the particular weight value or height value, right? So in this case, only the difference will matter when predicting the diabetes, right? So in that case, this kind of blindness is actually suppressing these unrelated informations or irrelevant informations to our classes intentionally, right? So those blindness is actually imposed intentionally through our model, right? So that is not actually a bad thing. That is actually a good thing, right? And that kind of blindness is also used in maybe principal component analysis. Yeah, so all these, the portion of the information that is irrelevant or that is not helpful in predicting a particular kind of target variable, so those information should be suppressed, right? And those information could be actually some measurement noise, for example. So if you just measured a maybe voltage of your electricity or battery or your maybe CPUs and so on by just proving through some electrical devices, and you measured some voltage patterns over time, and then that will always involve some noise through some measurement, right? And that measurement should be suppressed in order to obtain the real signals or true signals, right? And how do we suppress that part? Okay, so that is through this kind of linear transformations, for example. So that was also kind of representative example of using maybe principal component analysis. Okay. So those principal component analysis, widely used the justification of using that. I mean, that is one method of a dimension reduction, right? Dimension reduction. So it is actually dimension reduction. I mean, the neural net is a dimension reduction because we reduce the dimensionality from 3 into 1, right? So this dimension reduction is actually suppressing some irrelevant information for our task. Okay, although PCA is not aware of our main task, whether our task is to predict diabetes or our task is predicting a person's maybe other disease and so on. So PCA has its own criteria to suppress those noisy informations, but anyways, you can think of those suppressing is actually a good thing for our classification or our own task. Okay, so any questions so far? Okay, and then let's take a break until 12:05. Then let's resume after that. 안녕하세요.
저는 그대로 그게 다 우리가 보면 둘다 그랬어요.
놀리지. AI 블랙. 아, 이게 뭐야?
아 정말 그런 거 없어. 외우면 돼.
예. 네. 10분 보고 나가야지. 예. 과목마다 대답집 따로 써달라고 처음처럼 말해주고 다시 다 비켜가지고
그런 거 말해주면 될까? 아니면 다 제 아버지 공부 졸업 말만 통해서 나온 적 있어요. 인생에 다 나온 적 있어요.
그치 뭔가 잘안 맞고 근데 이게 뭐 우리가 가축 좀 늘어나면은 들어가게 오늘 점심에 이걸 못 해.
나 점심 먹고 있어.
나 오늘은 나도 그렇게 하는데 그 과에서 근데 그 전에 홍보병도 좀 하고 있어요.
공부에 너무 좋은데 뭐 그렇지. 근데 말이 그렇다는 거 진짜 아직도 도움이 되겠네.
케이스가
네.
인크리먼트에 블라인드하다라는 게
네.
어떤 의미가 있어요?
그거는 그러니까 이제 아까 뭐 얘기했던 것처럼 네. 요 인크리멘트라는 건 이제 요걸 얘기를 한 거예요. 그러니까 오리지널 벡터가 있을 때 거기다가 이제 뭔가를 더해도 어떤 특정한 벡터를 더해도
근데 이 오리지널 벡터도
네.
어떤 특정한 스페시픽한 벡터여야지만
그렇진 않죠. 그러니까 이거를 네. 요 x가 어느 벡터든 그 벡터에 대해서의 매핑 값이 있었다라고 할 때 그 벡터를 그 주어진 어떤 벡터든 간에 거기다가 어떤 이 널 스페이스의 스케일러 멀티플을 더하면 뭐
근데
그거는
이 x는 그러니까 이게 그러니까 이거의 멀티플리케이션이
네.
어떤 특정 벡터나 이렇게 값을 가져야지 지금 인크리먼트에 블라인드 한 거잖아요.
네.
근데 그러면 이 x는 눌 스페이스가 아니라
그렇죠.
이거의 컬럼 스페이스에 속해 있는 x인 거 아니에요?
컬럼 스페이스는 저기 그 아웃풋, 그러니까 이 아웃풋 벡터가 이제 살고 있는 스페이스를 의미하고요. 일단은 그러니까 이 x는
네.
이제 인풋 혹은
아.
이제 정의역에 살고 있는 벡터고 일단은 그러니까 w 곱하기 어떤 주어진 어떤 벡터도 상관없어요. 그 벡터 x에 대해서 아웃풋이 뭔가는 있겠죠.
네.
그러면 그 뭔가 아웃풋이 있을 때 이 값을 여기 x에다가 뭔가를 더해도 그 값을 바꾸지 않는다는 뜻이에요. 그래서 뭐 인센서티브, 뭐 블라인드라고 하는 이야기.
다시 한 번만 해주세요.
네. 그러니까 이 x가 그러니까 어떤 벡터 x가 주어졌을 때 그 벡터 아웃풋이 그러니까 w가 정해져 있고 어떤 x가 뭐 어떤 거든 상관없지만 어떤 특정한 벡터가 주어졌으면 무슨 아웃풋이 나오겠죠.
네.
그게 스칼라든 뭐 벡터든 상관없어요 사실.
네.
그러면 그 아웃풋이 있을 때 이 x라는 벡터, 그러니까 주어진 벡터 어떤 벡터도 상관없다라고 이야기를 했고 그 벡터에다가 어떤 스케일 저기 그 널 스페이스에 들어가 있는 벡터 중에 어떤 걸 골라서 스케일러 멀티플을 해갖고 얘한테 더해준 어떤 새로운 인풋을 구성을 하면 그게 원래 갖고 있던 아웃풋이랑 항상 똑같이 나온다.
원래 갖고 있던 아웃풋이랑 똑같이 나온다는
네.
얘기는
그러니까 이 뭐 과체중 얘기를 더 하면 이제 어떤 사람이 있어요.
네.
뭐 어떤 사람이 지금 과체중의 정도가 30이에요.
네.
근데 그 사람의 벡터에다가 키와 몸무게를 똑같은 값을 뭐 어떤 값이든 똑같은 값을 더하면
네.
새로운 사람이 되잖아요. 그러니까 새로운 사람의 피처 벡터로 생각할 수가 있고
네.
그 사람의 과체중의 정도는 이전 사람의 과체중의 정도랑 동일하게 유지가 된다.
그러면은 이 x의 이 WX를 마이너스 100을 만드는 이 x가 이루는 스페이스는 이 W와 이러한 x 플러스 인크리먼트를 했을 때 값의 변화가 아예 없다라는 거죠. 그러니까 거기
아웃풋에서
결국에는 이 x의 스페이스에 이루는 수많은 벡터들이 뭐 다른 특징을 가지는 벡터다라고 말을 못한다라는 거죠.
네, x는 x 자체에 대한 특성은 지금 여기서는 고려는 하고 있진 않아요. 그러니까 x는 그러니까 어떤 3차원, 그러니까 3차원이면 어떤 3차원 벡터든 다 된다라고 가정을 하고 있는 거예요.
근데 WX는 마이너스 100이라고 만드는, 그러니까 W가 정해져 있다라고 하면은 이거 있고 어떤 특정 값을 만드는 X는 서브셋이 그 3차원 전체에서 일부분이잖아요.
근데 우리는 이거에서 출발하는 게 아니라 이 값은 어떤 값이든 될 수 있고 우리는 여기서부터 출발을 하는 거예요. 어떤 인풋을 고르고 어떤 특정한 매핑을 하면 그거에 대한 아웃풋이 결과값으로 나오잖아요.
네.
네, 그러니까 인풋을 자유롭게 내가 바꿔요. 그러면 뭐 그에 따라 결과값도 뭐 이래저래 바뀔 수 있겠죠. 일단 그 세팅을 들고 와서
네.
그러면 여기서 이 프로세스에서 x를 고르는 과정 중에서는 어떤 제약점도 들어가 있질 않았잖아요. 그죠? 그러니까 그렇게 이제 자유롭게 고른 x를 가지고 이런 식으로 더하면 네, 그 벡터가 가지던 아웃풋 값이 바뀌지 않는다. 그러니까 100이라는 값이 주어져서 그 100을 일단은 아웃풋으로 만드는 x를 찾아서 지금 그런 세팅이 아닌 거죠.
그러면은 근데 A는 결국에는 이 W의 널 스페이스의 원소인 거잖아요. 근데 만약에 이런 X의 자유도, 그러니까 X부터 시작을 하면은
널 스페이스는 따로 찾고요. 그건 따로 찾아야 돼요. 따로. WX equals 0라는 방정식을 풀어서 따로 찾아야 되고요. 그 방향들은.
그러면은 A가, 그러니까 A는 그러면 픽스가 되어 있는 거잖아요. W가 정해지면은.
네.
그러면은 X가 자유도가 있다고 한들 이 값이 아웃풋이 변하지 않는 X 값들은
아니죠.
정해져
X는 자유롭게 내가 고를 수가 있고 그 자유롭게 고른 하나에 대해서의 아웃풋도 뭔가 있을 건데 그 매핑 관계를 그 x라고 자유롭게 고른 x에다가 내가 어떤 그 널 스페이스에서 뽑은 어떤 벡터를 적당히 더하든
저에도 상관
네. 매핑 값이 변하지 않는다는 뜻이에요.
하나 더 있는데 그럼 뉴럴 네트워크에서 블라인드가 나쁜 게 아니라고 말씀을
네.
하셨잖아요.
네.
근데 그게 좀 잘 이해가 그러니까 안 나쁜 것도 모르겠고 나쁜 것도 모르겠고 그냥
그러니까 블라인드라는 거는 이 정보의 이제 차이가 그러니까 실제로 예를 들면 160과 60kg인 사람과 185와 85kg인 사람은 이거는 정보가 다르잖아요. 다른 정보를 일단 뉴럴넷의 한 레이어를 통과를 시키면 이 다른 차이를 이 뒤쪽에서는 전혀 모른다는 거잖아요. 그러니까 어떻게 보면 이 어떤 내가 갖고 있던 오리지널 정보 중에 일부가 유실 혹은 소실이 된 거예요. 그러니까 이 뒤쪽 뉴럴, 이 뒤쪽 레이어에서는 그 정보를 못 보니까 그 차이를 더 이상은 볼 수가 없어요.
그러면은 트레이닝 셋에 대해서 만약에 어떤 이유 때문에 그렇게 그러니까 옵티마이즈를 해도 널 스페이스의 이러한 것들에 의해서 하면은 그냥 아예 학습이 안 됐다라고 보는.
그러니까 널 스페이스가 어떤 의도적으로 우리가 배워야 되는 널 스페이스. 그러니까 우리가 블라인드한 정보가 실제로 클래시파이어에 실제로 도움이 될 수가 있는 거예요. 그러니까 특정한 키가 크든 작든이 중요한 게 아니라 네. 그 차이만이 중요한 거라고 하면 특정한 키가 얼마다라고 하는 그 특정 정보는 우리가 날리는 게 더 좋은 거죠. 뒤쪽에서 클래시피케이션 할 때. 그러니까 그런 식으로 뭔가 이제 불필요한 정보 아니면 괜히 혼란만 줄 정보라고 해야 될까요? 그런 것들을 의도적으로 뉴럴넷이 그 옵티멀 파라미터라는 게 그런 정보들을 의도적으로 이렇게 인센서티브하게 만들어주는 과정.
그러니까 그런 정보들이 인센티브한 파라미터를 찾아 나가는 건가요? 옵티마이징.
네, 그렇죠.
맞아요. 조금만 더 생각해볼게요.
네. 질문이 뭐 있었어요?
아까 그 디멘션 n 디멘션이면 그거에 널 스페이스는 n 마이너스
네.
이런 그 부분은
그 부분이요? 그 부분은 그러니까 우리한테 주어진 저 W가 이제 로우 벡터, 그러니까 한 줄짜리 벡터로 구성되어 있을 때, 그러니까 아웃풋이 이제 원 디멘전일 때를 얘기한 거예요. 그리고 그 상황이 이제 아웃풋이 이제 원 디멘전으로 나오는 상황이 우리가 이제 이야기하는 이제 리니어 클래시파이어의 일반적인 상황이기 때문에. 네. 네.
탄시랑
탄H?
네.
네.
시그널이랑 클래시파이어를 바운더리가 수렴하는 속도가 좀 차이가 크게 나는.
탄H랑 시그모이드랑요?
시그모이드는 웹쪽이 그래도 2000번 정도 돼야 2000번이나 나오는 것 같은데 그게 왜 차이가 나요?
왜 나냐고요? 딥러닝에 대해서 조금 아나요? 공부해본 적 있어요? 그게 이제 탄H 같은 경우 시그모이드랑 탄H랑을 비교하면 그레이디언트 베니싱이 탄H가 더 이렇게 급격하게 기울기를 갖기 때문에 베니싱이 조금 덜 해요. 아마 그래서 그런 게 아닐까 싶어요. 오케이. So, related to the previous discussion that we had about having n-1 dimensional null space, so that case was corresponding to the special case of having W as just a single row vector where we have just a scalar output, okay, one-dimensional output, right? Because that situation is just a common kind of scenario when using the SVM or logistic regression or any other linear classifier, right? Because we just obtain a scalar output that will be a target value in the case of a regression, or after passing it through the sigmoid, and then our target value, or the probability of being positive class, right? So that will be our target value. But still, we deal with one single scalar value as an output, right? Because the predicted, target, value of our prediction is always one-dimensional value. Although, our in the case of generative model, again, in that case, our target value will be composed of really high-dimensional vector, right? Okay, and then also, so in this particular case where we generate one single scalar value as an output, and then the null space is an n-1 dimensional space, and then let me just extend output into two-dimensional vector, and then maybe input is a five-dimensional vector. Okay, so in this case, this is our W and X, and in general, the dimension of the null space, or the span, this null, how many vectors do we have? How many kind of vectors that has a different direction do we have for our null space, right? So typically in this case, so it is kind of related to something called rank theorem or something like that. I'm not sure about the exact name of that theorem, but so in this particular case, Wx should be equal to 0, right? So that x satisfying this equation will be our null space, right? So in this case, so we can think of, extend it into the current example. So in this case, so W transpose and x, and we have to satisfy this single equation. So our x should be perpendicular to the vector W, right? And vector W, we have only one vector W, of course, but in this case, we have to produce zero vector as an output, where we have output is two-dimensional vector, right? So in this case, still we have to produce zero vectors, and that means this guy and this guy, and we can, this guy and this guy should produce zero, right? So our vector x should be perpendicular to the first vector, and also it should also be perpendicular to the second vector as well, because it also has to produce zero, right? So we now have to, our null space vector should be perpendicular to two vectors, right? So if these two vectors have different directions, and then all the possible vectors that are perpendicular to those two vectors that has different directions in the five-dimensional space, because this guy is living in five-dimensional space. So in this case, what will be the dimension of the null space, or how many different vectors do we have to form our null space? So we have five-dimensional space, and then we have two particular vectors that is defined by each row of our matrix W, right? And our vector x should be perpendicular to two different vectors, right? And then, we have like 3 degrees of freedom, or 3 different directions remaining, so that we can have 90 degrees with each of these two given vectors, right? So it's like if this number was n, and this number was m, and then it means this matrix is m by n, because output is m-dimensional and input is n-dimensional, right? So in this case, the null space dimension, or the number of different direction of vectors that will form our null space, is n minus m, right? But it's not always true. I mean, we used a assumption here that these two vectors have a different directions. But what if those two vectors having the same direction? So for example, in the case of 1, 2, 3, and maybe in this case, we were able to find two different directions. They will produce 0 in this equation, right? But in the second case, if it is different directions, maybe 1, 2, and maybe 4, and certainly the second row vector will have a different directions from the first vector, and in that case the null space will be just spanned by one direction, one vector, right? But there is a special case like this. So in this case, even though we have to satisfy this equation so that this guy is perpendicular to the first vector and the second vector, I mean two different vectors, but those two vectors have the same directions, right? And so it's in this case, the null space will also have, still have the dimension of 2. But in general, if they are, 네. 네네.
저 경우에 널 스페이스가 2차원이라고 하시는.
네.
그러니까 저게 3차원에서 2차원으로 가는 거니까 3차원 3 마이너스 랭크가 되는 거 맞죠?
맞아요. So this M should not really be M. It's rank of our matrix W. Okay. What is the rank of a matrix W? So that is the number of linearly independent columns or the number of linearly independent rows of a given matrix. So that is the rank. So in this case, I mean, the rank is defined by using either columns or rows. So they are actually the same thing, although I'm not going to prove it, but that is related to finding out the pivots and the echelon form, and maybe if you heard about the Gaussian elimination to solve the linear equations or linear systems, and that is related to this thing. Anyways, so the number of linearly independent rows or the number of linearly independent columns in the same matrix should be the same. Okay, and that same number is called the rank, and this rank, and thus this rank is smaller than or equal to, like, minimum m comma n, right? So here m is 2, which is the number of rows, and the number of columns are 3. So the rank is always smaller or smaller than or equal to 2. Okay. But anyways, if we consider the rows, I mean, point is that it doesn't matter if we just consider rows or columns. Okay, and then the number of linearly independent vectors within rows or columns, that will be called the rank, and that will be the same number. Okay, when considering rows or columns. But anyways, so in this case, if we consider rows, and then if we have 2 rows, and then these 2 rows have actually 1 linearly independent rows, right? And so that number is a rank, right? So it should be 1. Any questions so far? Okay, so we studied the range and the null space, and I kept using the term dimension, right? So typically the dimension is simply the number of elements given in a given vector, right? So if we consider three-dimensional vector, yeah, I just mentioned it as three-dimensional, right? So yeah, simply that is actually the same as the number of elements in our vectors, but dimension has also a little bit more mathematically fancy kind of definition of number of linearly independent vectors that spans the given subspace or given space. Okay, again, we should be first given a particular set of vectors. Okay, set of vectors that is typically infinite number. I mean, that set of vectors will contain infinite number of vectors, and given that particular set of vectors, how many linearly independent vectors do we need to entirely cover up this given set of vectors by using the linear combination of these set of vectors. Okay, so yeah, let me just give an example. So it is actually R3, right? So in this case, when talking about the dimension, we have to first consider the given set of vectors. And what is the given set of vectors? Typically, when talking about this R3, and then we consider all the possible these three-dimensional vectors, where those three values can be any numbers, right? Real numbers. We can also consider complex numbers, but yeah, in machine learning or at least in computer science domain, we don't consider the complex numbers, okay, typically. And also our neural nets or maybe linear kind of classifiers or things like that will only assume we use real numbers. But there are some cases of using complex numbers. As far as I know, in other domains of maybe electrical engineering, when doing the frequency analysis and some other things, and then they heavily use complex numbers as well. So those linear algebra is easily extended to just handling complex numbers. But throughout our class in this semester, we just you can just safely assume that we use just real numbers. Okay, so this R is actually representing the real numbers. So three-dimensional complex number is written as this. Okay, so we are given the set of all the possible three-dimensional vectors that is composed of these three numbers, and then how many linearly independent vectors do we need in order to represent this set of vectors, okay? Which means that given any three-dimensional vector, that was selected or chosen from this given set, and then how many linearly independent vectors to represent any given vectors from this set. Okay, so that is like this. I mean, this is one particular set of bases. Basis. So that. Okay, so this is a really simple case, and that is called the standard basis. But suppose you are given any number, 4, 3, maybe 6, then this vector is always represented as a linear combination of these three vectors that has the linear combination coefficient as this, right? Okay, so those three vectors are linearly independent, and also using only these three vectors, we can represent any given vectors from this given set of vectors. So that way, those vectors are called the basis vector of this given set of vectors, okay? And the number of basis vectors is called dimension of this given subset of vectors. Okay? And so, so looking at, when seeing these three vectors, and that three vectors are just the same, having the same number of elements in our vectors, right? Because we only we just consider this one hot vector, or this is called the standard basis vectors. Okay, but those number of standard basis vectors will always be equal to the number of, this number of dimensions, or this number. Right? So that way, we can just apply this fancy definition of dimension. Okay, defined when given this particular subset of vectors. Okay. Okay, but there could be some other cases where we have some smaller set of vectors, but still living in this R3, right? So our subset of the vectors is still belonging to this three-dimensional space, but if we just have a alpha is any real number, so in this case, our given subset of the vectors is just a single line, right? So in this case, picking up whatever vectors from this given subset of vectors, and that subset is represented as the linear combination of a one single vector, right? So that way, this subset of vectors has the dimension of 1, because the number of basis vector that we need in order to represent any vectors as a linear combination of these basis vectors. So that number is 1 in this case. Okay, so that is the definition of a dimension. Okay, so I'm gonna just skip these. Okay, and then you guys know the matrix inverse, right? Matrix inverse. So matrix inverse of a given matrix is denoted as A to the power of -1, or it's called the A inverse, and an A inverse should satisfy this equation, which is when multiplying on the left of the original matrix or on the right, it should produce the identity matrix. And so this inverse matrix, invertible matrix, is only defined for the square matrix. So that means if we are given the rectangular matrix. So you guys know the difference between rectangular or the square matrix, right? So if it has the same number of rows or columns, and then it is called the square matrix, but it is having a different number of rows and columns, and then it is called the rectangular matrix. So whether a matrix is invertible or not is only, that only makes sense for the square matrix. Okay. So for rectangular matrix, whether it is invertible or not, it doesn't make sense. Okay, so that means actually that person discussing about it is actually not knowing the linear algebra, linear algebra properly. Okay. So invertibility, whether the matrix is invertible or not, is only defined for the square matrix, and also our inverse matrix is also square matrix. So given the matrix A being 3 by 3, and then our matrix inverse of it will also have the same size. Okay, and if we have a 3 by 3 matrix, and then suppose we found some matrix that produced identity matrix, which is also 3 by 3, and this matrix. Okay, so in more detail, when you found this matrix where you are given matrix A and some matrix X that has the same size of 3 by 3, and then found the identity matrix that has the size of 3 by 3, and then this X is called the yeah, it is not really an important term, but it is called the right inverse, because yeah, it was multiplied on the right and then produced the identity matrix. And also we can also think of some possible matrix Y when multiplied with the same matrix on the left this time, and that produced the identity matrix as well. Suppose you found this matrix Y or matrix X. Okay, so it turns out that, although I'm not going to prove it, but you can take, you can just take it as granted. But once you found the solution for this equation for X, and then that will be unique, uniquely defined. So you cannot find multiple different matrix X for whatever given matrix X. Okay, and also this equation will also have the unique solution, or it may not have any solution at all for this matrix Y. Okay, so in that case, your matrix A is not invariable. Okay, but anyways, suppose you found the solution for Y in the upper equation, and that matrix Y will be unique. Okay, so you cannot find two different matrices that satisfies this. Okay, so for each of them, the solution will be unique. And also, more importantly, the solution between those two will always be the same. Okay. So that is actually not trivial to prove. Okay. So I tried to find some proof from the internet, but yeah, there are some discussions about it. But yeah, to my knowledge, I didn't properly understand it. So yeah, let's just take it without justification about it, or rigorous proof. But if you found it, please feel free to let me know. Anyways, the point is that there is a unique matrix that satisfies either of them, and if one matrix is satisfying this, and then the other equations will automatically be satisfied. Okay, so there is another non-trivial kind of a statement, but yeah. So suppose you found the solution on the upper and another solution on the lower matrix, and that should be the same. Okay, and another kind of a statement that I'd like to make is that suppose you found the solution on the upper equation. Okay, and then that solution is unique again. Yeah, so that is again unique, and that solution will automatically satisfy the lower equation. Okay. So if you found, in other words, if you found the left inverse of a particular matrix, and that will be your right inverse. Okay. Okay. So that is the definition of the inverse matrix. And and regarding this inverse matrix, in maybe NumPy or maybe linear algebra package available in the Python, there is a function called the inv. So if you call this function inv of a given matrix as an input argument, and then it should it will give you the inverse matrix of an A. But in reality or in practice, you actually will have, there will be no cases that you will actually call this function. Okay, so so it is a little bit vague explanations, but there is almost no cases that you will need this inverse matrix explicitly. Okay, so this inverse matrix will always be used to be multiplied with some other vectors or matrix. Okay, so for example, suppose you want to find the solution for this, So we have an A which is a square matrix, right? And then we are given B here. So these two are constant matrix and vector, and our variable is X, right? So in this case, if A is invariable, and then A inverse times B will be our solution vector X, right? And so in this case, we have a inverse matrix A, but it is not explicitly used, but it is always multiplied with some other vector B, right? Okay, so that way we don't need to obtain this inverse matrix explicitly, but it will be always used as a part of some product between this inverse and also another matrix or vectors. So in this particular case, we want to use, you have to use this function solve. Okay, so that is also another function included in the linear algebra package or library in Python. So if you just give an input argument of A and B in this manner, and then it will always give the this output. Okay, so the difference between this and this is that so in this case, the typical way will be something like this. So in this case, we are explicitly obtaining this inverse matrix first and then multiply with the B. Okay? But in this particular case, this A inverse is not obtained independently, but this product between inverse and the B is computed. Okay. So let me just give a really one simple example of why that is used that manner. So let's think of this equation. So you guys will know that the solution will be 2, right? But in this case, suppose we just obtain the inverse explicitly. Okay, so A is just a 1-by-1 matrix of having 3, right? So in this case, what do we mean by obtaining inverse explicitly? Okay. It is like this, right? So typically it's related to just the approximation used in our computer, because we always represent a particular number using a finite number of bits, right? So in this case, the computer will represent this value as this number, right? But it has to be represented as the finite digits or bits, right? So in this case, if we just compute inverse of an A times, so this is our B, right? So in this case, the resulting value will be maybe 1999 and maybe 9, or maybe not 8 but 99 and so on, right? And so it will be represented as a finite number. So in this case, it will not produce 2 exactly, right? Yeah. So what do we mean by not explicitly forming the inverse, but instead computing this A inverse B, right? So in this case, instead of producing this value of 1/3, in this case, we will just do the computation of 6 divided by 3. So we will produce, or we will perform this computation, right? So in this computation, the computers can produce this number as the true number as 2. Okay. Okay. So in other words, my point is that if you explicitly inverse matrix, if you explicitly form the inverse matrix, and then it will have the potential problem of introducing some inaccuracy or this kind of a approximation, okay, because of this kind of division by something. I mean, division of 1 by something, okay. But if you just use this representation, and then you can sometimes avoid it so that you can have a better or more accurate number as a resulting value. Okay, and in almost all the applications that involves this inverse matrix, and the inverse matrix will not be used explicitly in any cases. Okay, so in all of the applications that you will just experience, then this inverse matrix will always be multiplied with some other vectors or matrix. And what if we want to obtain this? For example, A and X equals B. So A is maybe 3 by 3 matrix, and X is maybe 3 by 2 matrix. And then what is the size of B? B is 3 by 2 matrix. So this is a slight extension from the linear system of having a single matrix, a single vector, and also single vector in the place of B. Okay, so between these two, I mean, if you have this kind of equation where we have a matrix as our variable and B part as also a matrix, okay, in this case you can just simply just use this matrix B in this function solve. Okay. Okay, so yeah, so there is no problem of having a matrix on the B part when using this solve function. And this function, I mean, this equation is actually just a collection of two independent linear systems. Okay. So we have this matrix, and then let's just think of multiplication with the matrix on the left and this column vector, and then the it should be like this, right? And then it will produce the first column, right? And then we have a second column over on here, and then that will produce the second column, right? So this is our entire variable matrix, and that variable matrix, it can be divided separately into column by column. So the first column will produce the first column of the given matrix B. Okay, so that way we bring this matrix A, and then this guy, and then also this guy. So that is one linear system, and then the second linear system is this guy times this being equal to this, right? So that way those two linear systems are entirely independent of each other. Okay, so okay, and let me add one more comment. So in this particular case, I mean, it's a so easy example, so we can easily understand this kind of division process. But in more general cases, in this general cases of having matrix, and maybe this case, matrix and vector is equal to a given vector B, right? So in that case, what do we mean by computing this A inverse B without explicitly obtaining inverse of inverse matrix A, right? So in this case, how do we obtain this vector X without explicitly forming the inverse matrix? So it is just a Gaussian elimination, right? finding the pivots and doing the row operations, and that way we obtain this vector x, right? Okay, so any questions so far? Although the explanation is a little bit vague, but yeah. Yeah.
Explain more about Gaussian elimination.
Gaussian elimination. So it's basically a way of eliminating the variables from our equations. So how do we solve this equation? So there are 3 different ways of solving this equation. I mean, from our knowledge in middle school, maybe. 뭐였죠, 그게? 네? 그렇죠. 가감법. 또 뭐 있죠? 소거법? 소거법? 아, 소거법이 대입법이죠. 이름이 바뀌었나? 그래요. 네, 대입법 혹은 소거법. 또 하나가 뭐죠? 없나요? 네?
소거법하고 대입법 다르지 않아요?
달라요? 어떻게 달라요?
소거법은 이제 같은 텀 개수를 같게 만들어서 빼는 거고
그게 가감법 아니에요? 아, 가감법이 소거법이요? 아,
대입은 이제 한 변수에 대해 표현한 다음에
그렇죠, 그렇죠. 아, 그렇군요. 나는 소거법은 없었어요, 내가 배울 때. 네? 그래. 두 가지요? 아, 뭐 동치법 이런 것도 있지 않았나요? 이꼴로 만들어 뭐 하는 거 그런 거 없나요? 잘못 알았네. 네. But anyways, yeah. 가감법이 그럼 영어로 뭐죠? 소거법? 아, 오케이. 소거법이 variable elimination. 이겠네요. Okay, so Gaussian elimination is doing the variable elimination, right? So, but in this case, so we have some freedom or different ways of eliminating the variables with respect to like which variables to eliminate first, right? So in this case, in order to eliminate the first variable x, and then what we would do will be to multiply the first one as 4 by 4, and then subtracting it, right? And that way we can eliminate the first variable. But what about, what if we want to eliminate the second variable? And maybe we multiply with the 5 and the 2 to make the coefficient equal, and then subtracting them between them, right? So that is a way of a variable elimination, but Gaussian elimination is a special case of this variable elimination where we impose a particular order of variables to eliminate. So our elimination will always start from the first variable to the last variable. That is, we follow that specific order, right? So we don't just randomly eliminate variable in the middle out of maybe 100 variables. Let's just eliminate maybe 10th variable first. We don't do that, right? So in that case, we cannot actually build up our algorithm or like a consistent procedure to describe this elimination process, right? But anyways, so we first eliminate the first variable first, and the second variable second, and so on. And then another kind of a minor rule that we always follow is like we don't touch the upper equation, but we actually touch or multiply some scaling factor to the lower equation. Okay, so in this case, this is the upper equation or the first equation, so we don't touch that, right? And then this is the second equation, and so in order to eliminate the first variable at this moment, and then we have to multiply it with 1 over 4, right? So that way it will become 1. Right, and then we subtract it from it, right? Okay, and then the resulting equation, we actually replace that equation with the resulting equation. Okay, so if we subtract it from here to here, and then the resulting one will be something like this, right? So we obtained another equation basically by just subtracting from one equation by the scalar multiple of the another equation, right? And then even though we have one additional equations, but this is derived from the existing two equations. So instead of using this equation or this equation, we actually replace the second equation with this equation. Okay, and then now this guy is formed, and this, right? And then now this equation, from this equation we obtain x2 first, right? And then now we plug x2 into the first equation and so on, right? And that's how we obtain the first variable, right? So this is the variable elimination method, right? But let's just extend it into the case having a more number of variables. So we have x1, x2, and x3, and then some number, and also some number, x1, x2, x3, and some number, and so on, right? And in this case, where we have more than two number of variables and or equations, and then how do we impose this elimination procedure? So we don't touch the first equation, and at the same time we eliminate the first variable in the remaining equations or lower equations. But in this case, the lower equations is not just one, but the lower equations is this much, right? So all the remaining equations are those equations where we have to eliminate the first variable by using this guy, right? And then how do we do it? It's simple. So if it was 1 and if it was 4, and then we did a multiplication of 1 over 4, and then if it is this, and then we have to multiply its own scaling factor to match this number, and then subtract this equation from each of the lower equations, and replace each of these equations with the new equation, right, where we eliminated the first variable. So in that case, if we think of this process, we just eliminated the first variable, right? And then let's think of this part, okay, this part. And then these equations. So suppose we had 5 equations, and then we now have so let's say we have 3 equations, and then 3 variables, and then we eliminated the first variable in the lower 2 equations, and then we now have 2 equations, except for the first one that we didn't touch. And then how many variables do we have? We have 2 variables, right? So now from the 3 equations with the 3 unknowns or 3 variables, we now have one small number of equations with the one small number of variables, right? So we kind of effectively reduced or made complicated linear systems or set of linear equations into smaller or easier problems, right? So we do it recursively. So in this case, this is now our first equation, and then now we always select the first variable as the one that we have to eliminate, and then suppose it has 2, and then so all these parts will be eliminated, right? And then the resulting equations will replace these existing equations, right, as the form of all zero equations for the first eliminations with this smaller size of this set of equations. Okay, so this process will be done recursively until we have only one variables left and one equations left, and then we can easily obtain that last variable, right? And then it will be plugged into this upper equations, and in that case it has the effect of eliminating all the last variables, right? Because we just plugged a particular value into that last variable because we already obtained that value. Okay, and then from so this if this guy is plugged into this second equation, and then the remaining variable will be just second one. Okay, and then it will be plugged into all these parts, right? So it's like this is a forward pass, and then this is the backward pass. Okay. Forward pass is reducing the number of equations and the number of variables one by one, and then once we finally obtain the one variable and one equation, and then obtaining that particular value, solved that value, and then it will be plugged into upper equations, right? So that is the backward phase. So this is the Gaussian elimination. And but typically this process is done in this manner. So we bring this, we convert, for example, this guy, set of an equation that we are given into, what we call the augmented matrix, where we have only those coefficients or this bias value, right? So in this case, what is the meaning of this guy? Multiplied by 1/4, and then subtracting it and replacing it. Okay, and then in this matrix we just multiply this row by 1/4, and then subtracting it and replacing the second row with the new one, right? The first one is untouched, and the second one is becoming, right? So that is equivalent to this guy, right? So this kind of thing is a row operation or Gaussian elimination, right? And at the end, where we have only one variable and one equation, and then how do you obtain that solution of that variable? It is just simply divide this value by this, right? So that is equivalent to 1, 2, 3, and scaling. Okay, scaling this equation into 1 times x2, and this guy divided by this guy, right? And then the equation, this equation can be viewed as being converted into the new equation, which is still having 0 and 1 here, and what is the number? Is it 2? 2. Okay. And then what is the backward phase? Plugging, from here we now obtained x2 being 2, and then we plug this guy into all the upper equations, right? And then how can we represent it? As this kind of matrix operations. So So 1, 2, 3, and 0, 1, 2. And then in this case, the upper part is also done in this matrix as another type of a row operation. And how we do it is as follows. So we just, we still do the variable elimination. Okay, variable elimination in this case. So x2 being 2, and then plugging this guy into here, and then x1 times 4 equals 3, right? And so typically x1 is obtained as -1, right? But can we represent it as also a variable elimination process? x1 plus 2x2 equals 3, and 0x1, yeah, it is already eliminated in the first step, and then x2, 1 times x2 being 2, and then how can we perform the variable elimination? And now we are doing the reverse order, in the reverse order from the bottom to the top. So now untouched equation is this guy. Okay, by using that, we change the upper equations by just scaling with some value, and that scaling value should be 1/2, and then subtract this guy from this upper equations and replace that equations, okay, that row. And then, yeah, it is represented as the second, I'm gonna write the second equation first. So this is the untouched or unchanged second equation. But what about the first equation? First equation is, so it is 1 and 1x1, because it's 0. It's yeah, whatever multiple. Yeah, yeah. If we just subtract this guy from the first one, yeah, it doesn't change. Yeah, so here there is a slightly different process, and the scaling is done in the second one. Okay, so here we don't just scale the first one, but easier way of scaling is the first one, because we already made the coefficient for this second variable as 1 in this lower equation. Okay, so we do the scaling on this lower one, and then subtract it from the first equation, and then replace this old equation with the newly obtained equation. So so it times 2, and then it will be 2 times x2 equals 4, and then subtract it from the first one, and then it will be 1 times x1 plus 0 times x2. This guy should be 0, right? Because we eliminated this, right? So that will be -1, right? So now, yeah, representing it as the matrix form, and then the second equation, the lower one, was not changed at all, but the first one was replaced as 1, 0, and -1, right? And then, yeah, we now obtained like x1 being -1 and x2 being 2, right? So so this is how we perform the Gaussian elimination. So so in this general cases, using the upper one, which is not touched, and then in all the remaining equations, we eliminate the first variable, right? So that's how we reduce the equation, the size of our problem. Then overall, if we keep doing this, and then the matrix will have this kind of a shape. For example, having 3 equations and 3 variables, and these are the variables x1, x2, x3, and this is b, and this is equation 1 and equation 2 and 3, and then there is some value over here maybe. So in this particular case it was 1, but yeah, it can be other than 1, right? So if it was maybe 3, okay, then it will be like 3, but still we can just so if it was 3, and then again the first one is not touched, but what is the corresponding scalar multiple of the second one? It is just this guy, 3 over 4, right? So only that scaling part will be, will change. Okay, so we will always have 0 on this part. And then now we obtain one size smaller equation. And then suppose this value was what? In this particular case, it was 3 over 4. I mean, the point is, we will obtain some non-zero value. And this part is 0. I mean, for this part, I mean, we only have 3 equations, so yeah, it is still a simple case. But what if we have maybe 10 different equations, and then we have to remove or eliminate all the first variables in the lower equations and in the one size smaller set of equations, and then we do the same thing of making all these zeros. And so overall, we obtain this kind of staircase shape where those values are still non-zero, but this guy and the below that value, and this guy and the lower than that, we obtain 0 values. So this is called the what? It's called this echelon form. 뭐라고 했어요? 가우시안 엘리미네이션? 가우시안 폼이라고 그래요? 네, echelon form이라고. So this particular form is called the echelon form. Yeah, I mean this whole process is called the Gaussian elimination, right? And then now, when doing the reverse order thing, and then what we did over here was, once we obtained one equation and one unknown, and then we made this guy into what? So this guy was, in the previous case, it was 3 over 4, and this guy was 3 over 2, right? And then what we did was just scaling the rows, I mean the last row, so that we have value over here as 1, right? So we scaled that way. And then now, by just multiplying some, so suppose it was 4 and 3. And then we just multiply 3 and then subtract it from here to make this value as 0. And also we do the same thing to eliminate this last variable that we obtained, right? So in this case we multiply it by 4 and then subtract it. Okay, so in that case, in this kind of staircase shape, so this guy, and then eliminate all the lower one and moving to the one right and one bottom, and then this guy is now our first variable, and then removing all of them, then moving it, removing it, and then we reach the final one, and then using this, we first scaling it as 1, and then all the upper ones are removed or eliminated, right? And then we now move the upper one, and then this will be our last variable, and this guy will be 0. That means, except for this guy, all the left one or the right one are all 0, right? Because the left ones were eliminated from the forward path, and the right ones were eliminated from the backward path. And so this guy will have only non-zero on this part, but 0 on the left or right, and except for that bias value. And then we just scaling it into 1, and then we removed upper one. So if we do this kind of process, then we obtain 1, 1, 1, and 0 over here. So if we obtained maybe 3, 4, 5, and that means x1 being 3, x2 is equal to 4, x5 x3 is equal to 5, right? So this is Gaussian elimination process. Okay, so this is a high-level overview or big picture, yeah. So there are some more details about this Gaussian elimination process. So those details are like handling or considering, yeah, those cases where we have more number of variables than equations. Okay, more number of variables than equations. So what that means is, so the reality is not always ideal. So in this case, 3 variables and 3 unknowns, which will typically give us a solution. But what if we have maybe three variables but 2 equations, right? So that is certainly possible, right? So x1, x2, x3, and b, but only 2 equations. So in this case, so we have non-zero value over here, and then we can remove this guy, right? And then now we move on to this guy, but there is no lower equations over here, right? So now we have, we have to just turn to the backward path in this case, because we handled all the lower equations and reached the bottom. Okay? And then we can eliminate this guy as 0, but still we cannot guarantee those as a non-zero. Yeah. So in this case, the solution is not uniquely defined, right? Because intuitively we have 2 equations, but 3 unknowns, right? So in this case, we cannot. we have no way to obtain just a single equation that has some non-zero value, a non-zero coefficient assigned to only one single variable, and some value on the b part, right? So we have no way to obtain this kind of equation from these 2 equations from the perspective of this Gaussian eliminations, right? So in this case, the solution will be like not unique. So we have an infinite number of solutions, but but it is not always true. So the question is, if we have 3 unknowns and 3 variables and 2 equations, is it always true that we have infinitely many solutions? So we have some other special cases to consider. So for example, suppose this is the first equation, which means 1 times x1, 2 times x2, 3 times x3 equals 4, right? And then the second equation was something like this. So in this case, let's do the forward process, forward elimination. So using this, and then we multiply by 3, and then to remove this guy, right? And then the 1, 2, 3, 4 is not changed, but the second one is, so this guy is certainly removed. So it's guaranteed to be removed, because that's how we did, right? So that's the process that we did. And then unintentionally, so it was not our intention, but it actually happened that those values turned out to be 0, right? Through this process, right? But those value is turning out to be non-zero value, right? So in this case, the last equation, is 0 times x1, 0 times x2, 0 times x3 is -1. Okay? So there is no way to satisfy this equation by using whatever values of an x1, x2, x3, because their coefficients are all zeros, right? So we have no control over this equation. So in this case, even though we have 3 equations and 2 equations and 3 unknowns, but the solution doesn't exist at all, right? Okay, and then yeah, let me just consider just one more case in this shape. So so from this pattern, you guys can see that even though we removed only this guy, but unintentionally, I mean, it may happen that some other values also become 0, right? So in this case, this guy, I mean, in the forward pass in this case, and then we obtain 0, and then this guy will be our first variable, but that doesn't have, I mean, that has a 0 coefficient. So yeah, if we have more equations, and then by using 0, you cannot eliminate the corresponding variables in the lower equations, right? Because we simply have no variable in that equation, right? And also in the case of an upper elimination, so we reach it to the bottom, and then now we turn to the backward phase. But since this guy is 0, and so this guy cannot also be removed either, right? So it also may happen the case like 1, 2, 3, 4, and there is 6, 10, 11. Okay. So in this case, what will be the resulting Gaussian elimination process? 1, 2, 3, 4, and 0. And this guy became unintentionally also 0, right? And then it is 1, and then negative 1. Okay. So in this case, the second variable became 0, and so in this case, what will be the variable to use in the next step of Gaussian elimination? So certainly we reach at the bottom, and then now we have to do the backward pass. But the first variable that we use for our elimination process is not x2, but this x3, right? Because that is the first variable in the remaining equations, and so we actually use it to remove this guy. Okay, and then this guy, yeah, it is 1, 2, 0. So yeah, we multiply it by 3 and then subtract it from the first one. Then it is becoming 7, right? So in this case, yeah, we have no problem of obtaining x3 being negative 1 as a unique value, right? x3 is a unique value, but can we uniquely determine x1 and x2? Yeah, it is not possible because yeah, in this upper equations, we have one equations that involve both of x1 and 2 or multiple variables. So in this case, using this single equations, x1 and 2 or this multiple number of variables cannot be uniquely defined, and thus even though x3 is fixed as a unique value, but the entire solution set will be yeah, infinitely many, because we have many possible choices of an x1 and x2, right? So for example, maybe 3 and 2 will be our solution, because 1 times 3 and 2 times 2 will make 7. And we can also find some other examples, right? So it is 5, and then it is 1. So already, yeah, we found 2 different solutions while fixing x3 as negative 1, but by changing x1 and x2, right? Okay, so yeah, so this was a quick overview, although yeah, we spent some amount of time, but yes, there are a lot more things to know or study about this Gaussian eliminations in terms of the number of solutions. Yeah, so I strongly encourage you to study this this Gaussian elimination, or yeah, linear solving the linear systems in the linear, in the linear systems, especially in the undergraduate. It's not the end, right? Is it? Oh, yeah. Okay. So let me see. 언제 끝나는 거죠, 그죠? 네? 그래서 우리 10시 반에 시작했죠. 11시 45분, 12시, 1시 15분. 그러네요. 네, 이거 그래요. 네. Okay, so anyways, yeah, we covered the lecture 1. Okay, so yeah, let's wrap it up today. So let's meet next Wednesday. Okay, thank you very much. 네, 수고했어요.
이해를 약간 못한 부분이 있어서
네.
좀 약간 여기서 이제 이거 표현할 때 이 투 벡터 갖다가
네.
이 3차원이 표현한다고 생각하면
네.
어떤 말인지 정확히 모르겠어요.
네. 이게 보자. 네. 여기에서 이제 요 두 개 컬럼으로 이루어진 하나의 매트릭스가 있고요. 여기 이제 x1과 x2라고 하는 컬럼 벡터가 뭐 예를 들면 요 벡터 이렇게 곱해지면 그거의 이제 아웃풋은 그걸 이제 공역이라고도 표현하고 이제 공역이 이제 코도메인이라고 이야기하는 코도메인은 일단 3차원 스페이스에 있고요.
그래서 그 아웃풋이 이제 3차원으로 간다.
네. 근데 그 3차원 내에서 이제 한정된 부분에만 저 이제 펑션 아웃풋이 존재한다는 거죠. 그리고 한정된 부분은 저 두 개의 선에 의해서 이루어지는 그 평면 내에만 이제 존재한다는 뜻이 됩니다.
그 다음에 이거 이쪽에서 또 하나 궁금한
네.
게 이제 이렇게 두 개 곱했을 때 이게 처음 줄어들면서 이 두 가지 함수로 이게 표현이 가능했잖아요. 아니, 두 가지 벡터로.
네.
근데 이제 여기서 이 두 가지 벡터가 이제
네네.
고정이 되는 건지 아니면 이렇게 다른 게 막
오케이.
변경될 수 있는 건지.
변경될 수 있어요. 그러니까 이제 지금 우리에게 주어진 거는 이 1, 2, 3이라는 요 어떤 이거는 정해져 있어요.
네네.
근데 이거랑 지금 수직인 게 지금 요것도 있고요.
네네.
요것도 있고
네네.
굉장히 많잖아요.
네네.
근데 중요한 거는 뭐냐면 그러니까 이거는 굉장히 무수히 많아요.
네네.
가능한 거는. 근데 중요한 건 이걸 찾았고요.
네네.
이거랑 리니얼리 인디펜던트한 또 하나를 찾았어요. 그러면은 그 두 개의 리니어 컴비네이션으로 모든 애들 다 표현을 가는 모든
그
애들이
인디펜던트 두 개만 찾으면
맞아요.
모두 다 된다. 감사합니다.
중요한 포인트네요. 네. 뭐 사인요? 펜 혹시 있나요? 뭐였죠 이게? 네.
교비 신청.
네.
일단 사인해 주시면.
많은 이해 못한 것 중에 하나가 아까 이게 베이시스의 개수가 디멘전이라 하셨는데 아까 예를 들어주신 게
네.
베이직
네네.
베이시스를 쓰냐
네.
아니면 이것도 베이시스를 쓰면은 이것도 디멘전이 1로 치는 건가요?
요거 1, 2, 3이 그러니까 어디서 나왔나를 보면 여기서 나온 거죠?
네,
그러니까 네. 그러니까 우리한테 입력으로 주어지는 그 벡터의 부분 집합이
네.
그냥 이 3차원 벡터의 모든
네.
애들을 포함하는 뭔가 전체 집합 개념이면 그거를 이제 리니어 컴비네이션으로 모든 애들을 빠짐없이 나타낼 수
네.
있으려면 3개가 필요한 거고요. 근데 우리의 그 이제 그 벡터 부분 집합이 역시 3차원 내에는 있는데
네.
이거보다 훨씬 작아서 요 1, 2, 3의 어떤 스케일러 멀티플로만 표시되는 어떤 셋이 주어지면 이거는 이제
그럼 이건 디멘전이 1로 보는
네, 그렇죠. 이거는 여기 있는 모든 점들을 표현하는데 이제 필요로 하는 그 리니어 그 베이시스 벡터가 하나만 있습니다.
그냥 서브셋에 따라서 달라지는
네, 맞아요. 서브셋이 주어져야만 이제 그거에 대한 디멘전이 정의가 되고요. 그 다음엔 주로 이제 이 R3가 3차원이라고 이야기하는 거는 아까 얘기했듯이 그냥
전체로 보기 때문에
네, 기계적으로 이게 숫자가 3개이기 때문이라고도 이해할 수 있지만
네.
지금 이런 어떤 좀 수학적으로 조금 더 명확한 이런 정의를 따른다면 이제 우리한테 주어진 벡터 서브셋은 이 3차원 전체 집합의 모든 벡터를 다 의미하는 거고 거기서 이제 찾을 수 있는 베이시스 벡터가 이제 요 3개가 이제 필요하니까 그 베이시스 벡터의 개수가 3이니까 3차원입니다.
근데 실제로 뭐 컴퓨터 사이언스에서 할 때는
네.
이런 식으로보다 이런 식으로 더 많이 쓰니까 이렇게 생각할 수 있다.
아, 그러니까 이거랑 이거는 하여튼 주어진 입력으로
네.
주어진 벡터 서브셋이 다른 거예요.
아, 네.
네네. 그래서
그래서
그에 맞춰서 네.
네, 그 정의는
베이시스와
디멘션은 그거에 따라서
네,
달라지는
그렇죠. 네. 네.
교수님 그 다음 주도 그 휴강이고 다다음 주도 휴강했는데
네?
따로 보강
다음 주 휴강이에요?
추석이요.
아, 추석이 휴강이죠.
그 다다음 주는 개천절입니다.
그래요? 아, 그럼 우리가 앞으로 2주를 쉬는 거예요? 아, 그렇군요. 그 보강 관련해갖고 한번 생각을 좀 해볼게요. 어떻게 할지. 네. 그래요.